Can you hear me now? Hello? Can you hear me now? Okay, awesome. All right, so I'll start again completely. Sorry about that. So welcome to the first of what is hopefully going to be a very long series of tutorials on Grasshopper. I'm a Grasshopper user. I'm not necessarily the best YouTube user, it turns out. I usually just upload stuff. I haven't tried a live classroom before. So thank you for tuning in, and thank you for Sarah and Clovia for telling me that I was not actually streaming when I thought I was. So all good. So I'm going to just quickly delete some stuff that we need to go through again. But and you'll notice that I have the Bifocals component here, which is great. So the Bifocals component allows me to have the draw icon option on. So if you want to use icons, you can. So I have a point component there, and you'll notice that it has point at the top there, and it's also drawing the icon. So however you want to work, it's totally up to you. I don't mind. But it allows both people to follow along and look for the kinds of symbols that they're more comfortable with. So what's an attractor grid? So an attractor grid is a grid, obviously, that somehow is edited based on its attraction to a point or a set of other points. So looking at this Precedent, which I'm assuming is a bar in France somewhere, you'll notice that there's a whole series of timber bits extruding down. And the extrusion distance is dependent upon its distance to some imaginary point. Doesn't sound very complicated, but it's one of the kind of introductory kinds of algorithms that you learn to write when you're learning a new piece of software. And I'd like to highlight that this is aimed at new people that haven't really used Grasshopper before. So if you have any questions, or if you don't quite get something, feel free to put it through the chat and ask, because it's likely that other people that either come to the video later, I'm not sure I can fix the echo bit, Avinash, I apologise, I'll look into that for the next one. They might have the same questions, so feel comfortable asking anything to help you understand, and I will kind of stop everything and try and make it a little bit more clear. So what are we going to be trying to do? So what we're going to try and do is we're going to try, and this is a drawing that I prepared earlier in all my my glory, is, in short, we're going to have 2 points, okay? And we're going to apply this logic to an array of points eventually. But what we're going to do is we're going to try and draw a line between them, because that's like the most simple thing you can do, and the line is just hypothetical. And the relationship between these 2 points is always going to be definable by some number, which is the distance, right? So these points will always have a distance between them. And what we're going to try and do is use this number to transform or create some geometry around that point that somehow represents how close this point is to it. So, for example, the simplest thing I could draw would be a circle. And if I'm drawing a circle based on its distance to that point, you'll notice that, and I'm not the greatest circle drawer, but it would draw a circle that, touches that point. And as that point moves closer, so if I had, 2 points that were quite close to each other, it wouldn't take you very long to determine that the circle would be much smaller. And all we need to do is get that logic sorted, and then we just apply it to a lot of points. And because they're not affecting each other, and you'll notice that we can very, very quickly get, something that looks like the precedent that we're looking at in order to try and do it. So you'll notice that, each of these are a different height, but they're all based on their distance. And the smooth curving happens as a consequence of just the relationship of how calculating distance works. So it's actually quite a simple algorithm. Now, before we start actually using Grasshopper, we should do something that is actually commonly called pseudocode. And we want to do pseudocode so we have a plan. Now, I've got a notepad document open here, and I'm going to just think about the types of steps that I'd have to go through to produce this particular algorithm. I sound like a wizard. Thank you very much, Ankito. All right. So the first step is always the easiest, and it's like get some inputs. And we need to just get some pretty simple inputs. The first one is get some points. I'll do that in lowercase. Get some points to use for distance calc, short for calculation. And then the next thing is get a grid to also use for that calculation. Right? So we need to have a set of attractors and a set of and a grid, right, to make an attractor grid. The next thing we need to do is that, and this one's quite simple, get the distance, right? We need to get the distance between the points and the points on the grid, which is fairly simple. And then, if I can spell the correctly, that would be great. Third time a charm. After that, it's pretty simple, and this is like the most complicated step, I would say, if you don't have a lot of mathematics experience. I personally love mathematics. Is we need to do some math to change the effect to what we want. Now, what you want might be different from what I want, but you notice that, for example, with the drawing the circle, that if I just take the distance and use that, then the circles are always going to get bigger. But a common strategy is to actually do the opposite, where the circles get smaller, so the circles don't actually intersect on each other and create a jumbled mess, which is something that we should see fairly early into the process of doing these calculations. And then the fourth one is we want to drive some geometry with the math result. And that's pretty much the attractor grid, right? So we get some points, we find their distance, we do some math to make it like a little bit nicer, and then we can either extrude some rectangles or we can scale some circles or whatever you want. So, all right, let's get started. So I'm going to do a two-dimensional one, and then I'm going to move on to a three-dimensional one, just so it's super clear what we're doing, and then how we can begin to just subtly change the algorithm in order to get a very different effect. So heading back to Grasshopper, I'm going to just put a couple of points, probably 3 points, in the top right quadrant of my Rhino window. Now, again, I'm sorry that I've got a little watermark there for those watching live. I'll move that after the live video. Actually, you know what's probably better? I'll just move the entire viewport to this side here. So now it's not bothering anyone. All good. Everyone's a winner. So I've got these 3 points in Rhino, and I'm going to want to reference them into Grasshopper. And if you watch my previous tutorial on Grasshopper Basics, we're going to want to grab a point component, and we're going to want to right-click and set multiple points. And you'll notice that we have 3 X's appear on the in the Rhino window. The point component has changed from orange to white. And if I get a panel component from up in the input subcategory, and I connect it up, it has 3 reference points in it. Great. This is exactly what I expected the output to be. So that's working exactly as I think it should. And I know this might seem a bit slow and a bit boring at some points, but this is the kinds of behaviors you want to develop, because a lot of the time, you know, like with modeling software, people usually say, well, software in general, people usually say it's not working. But actually, what I find is it's quite common that you've asked it the wrong thing. Now, all good. So now we've done the first half of step 1. Now what we want to do is we want to make a grid. Now, if we go to vector, and under grid, there's a whole series of grid types you can make. But for the sake of simplicity, and because we're kind of trying to match the precedent image, I'm going to choose the square grid. Cool. Now, you'll notice that in the Rhino window, a grid of rectangles has appeared, along with a second grid that is a little bit paler. Now, the grid that's 1, 2, 3, 4, 5, 6, 7, 8 by 8 by default is a visual representation of the plane that the grid is being constructed from. So if I hold my mouse over the very first input for the component, you'll notice that it asks for a base plane as one of its inputs. So if I right click on that component and go set one plane, and I move it to here and I rotate it that way, and yeah, whatever, you'll notice that then I get a rotated plane that's centered around whatever plane I picked. For the sake of simplicity, we're just going to stick at the origin. That's where I picked that up from. And we're just going to work from there, and if you need to move something, you can move it into position yourself later. Awesome. So, here we are. Now, the next input is the size of the grid cell. So, I'm going to get a number slider, and I'm going to drag that in, and I'm going to plug that into the S. And you'll notice that now I can control the size of the grid system. Now, EX and EY are asking for the number of cells. And if you watched the video I was talking about numbers, this is why I kind of made it, because this only makes sense to be a whole number, right? You cannot have 4.5 cells. You either have a cell or you don't have a cell. So I'm going to get another number slider, and I'm going to go into its options, and I'm going to change it to be an integer number, and I'm going to make it a number between 1 and 20. And I'm going to copy and paste another one in, and I'm going to plug that into the Y. And what we notice is that, we can control the number of cells in each direction, along with the size of each of those cells. Now, here is where I feel like a particular problem can be identified. And that is that if I'm sitting there designing something with my 3 attractor points, and I decide that I want the cells to be smaller, but to have more of them, i.e. cover the same area, we kind of end in a problem, right? Because we don't have that power. We'll need to sit there and scale these points along with it. So say I'm working on this grid system, and I'm like, okay, cool. I have a point there, I'll have a point there, and I'll have a point here. And then I say to myself, actually, you know what? I'm learning how to use the move command, great. And I decide, actually, you know what? These cells have to be half the size. And then what I have to do is I have to select these points, and I have to scale those as well, which is really time consuming. So we should just slow down and try and do things in a slightly more intelligent way. And looking at this component, this always has to be a whole number, but this can be a fractional number. So I want to find a way to take this number, or this number, I don't really care which one you choose, and get it to define the size of the cell. And what I'm going to do is I'm going to actually use a division component. So under maths, I'm going to choose, under operators, I'm going to choose to do a, not an integer division, but just a normal division. And just to be very, very clear, it's there on the operators menu, and it's not this one, which the symbol is flipped the other way. It's the one right next to addition. Now, I'm going to plug the number 1 into the top. So I'm going to get a 20th by default, right? So the size of the cell will be a 20th, and there will be 20 of them. So the entire thing will fit in a 1x1 grid in Rhino, right? And as I change the number in the X, the size of the system in the X will change with it. You could choose to do the Y, whatever you want is okay. But now the next thing we're going to have a problem with is that maybe that's not what we want. Maybe we want to be able to control maybe we want to be able to say that the entire length of the attractor grid is say 50 units long. And to do that, all we need to do is actually take this number slider we made here and give it a max value. And it can be a real number, that doesn't matter. And now we can decide whatever the X dimension of our attractor grid is, along with the number of cells in that dimension. Is that super clear? Any questions before I start moving on to the next thing? I'm going to have to wait for the chat to catch up, and I'll keep going, but if you have any questions there, feel free to stop me. Now, another thing you might want to be able to do, which is just a slightly more robust version of what we just did, is instead of using this square grid, that we can use a rectangular grid. And plug the X's in, and then do a very, very similar thing for the Y's, in which we can also control the, by copying all of this and putting that down, we can plug the division into the size of the Y component and the number of cells into the number of cells input, the EY input, and you'll notice that now we can also control it in the Y direction independently to the X, giving you a bit more control. Now, I'm kind of happy with what I've got here. I'm going to make the size of the overall system 10 units by 10 units, and I'm going to make it a kind of a square, even though I could make it a something a little bit more complicated. All good. And now we've got our input and our grid. So we're done with step 1. So if we look back at our sheet here, get some points. We've got some points and we've got a grid. So now we're moving on to finding the distance between them. Now, there's a multitude of different ways that you might want to go about this. If we look at our rectangular grid component, and we pay a lot of attention to it. Sorry, I've just realized that the Grasshopper window can be stifling there. Issues when you do things on live. You'll see that it outputs grid cell outlines, and it also outputs points at the corners of those grid cell outlines. Now, we can sit there and try and build some geometry from those corner points, or we can try and take those cells and find their centers. Just to reiterate, I'll make a point component, and you'll notice that all the points are at the corners of these cells, like not particularly surprising. And you'll notice that if I get a curve component and I plug that in to the curve one, I get, and it might make a little bit more sense if I bake these out so you can see them when I select them and it's yellow, that it's a rectangle, or in this case a square, constructed from going between each of those points. Now, its center is not the center, like it's not those points, right? Its center is the average of those points. So one simple way that we can kind of get around this problem and say we want to scale these squares to be the geometry that we're manipulating is to find the square's center. Now, that shouldn't be too difficult. It's a curve, so I'm going to assume that it's in the curve category. And I'm going to click on analysis because it seems to be the thing that makes the most sense out of analysis, division, primitive, spline, and utility. And there we go. There's a component called Polygon Center. So find the center point average for a polygon. That sounds like exactly what I want. So I'm going to click on that and I'm going to drag that into our file. And I'm going to say, okay, I want the center for all the curves. Now, great. That looks like it's found all the centers. What we will realize pretty quickly is that it's outputting 3 different types of centers. Now, what it's doing is it's finding something called a centroid. And a centroid is not necessarily the center of an object, and there are multiple algorithms for finding them. And you might want to use a different type of center calculation based on different conditions. But here, what we're doing, the geometry is simple enough that all of these 3 centers are identical. So, great, we have our center point. Now, what we need to do is, if we look back at we think about our plan, we just need to find the distance between the center of the polygons, voila, and our points that we've defined previously. And I'm going to go back to the vector tab because points are a type of vector fundamentally. They're like a vector with a piece of geometry associated with it. And we're going to click on point because we're working with points. And you'll notice that there is a closest point component. Cool. So it's asking for a series of things. It's asking for a point to search from and cloud of points to search. I'm going to plug the Polygon Center into the first one, into the P, and I'm going to plug the point into the bottom one, the C. I'm going to move my point down here so it doesn't intersect when it doesn't have to. Don't cross the streams if anyone's a Ghostbusters fan. Now, this component will pop out the point that is closest, the index of the closest point, but also the distance to that point. Now that we've got that, we can ask it to do some sort of transformation, right? So if we look back at our typing, we're going to do some math, but it makes a little bit more sense to do 4 to then understand what 3 should be. So, all right, we've got it here. I'm going to just, in this instance, scale these squares based on their distance. And to do that, I'm going to go to the transform category and I'm going to choose Euclidean. No, I'm not going to choose Euclidean. I'm going to choose affine and I'm going to choose to scale the geometry. So I've got a scale component and it asks for 3 things. The first thing it asks for is the geometry I would like to scale. So I'm going to choose to scale the rectangles that I have constructed. And you'll notice that by default, it sets its factor to 0.5. The next thing we're going to do is look at the next component, center of scaling, which is set to 0, 0, 0, which we really want to be scaling these things from the center of their cells. So now you see that each individual cell is scaled by a half. And then we want it to respond to its the distance to its closest point. So we're going to plug it into there, and you'll notice that what we end up with is a bit of a garbled mess. And if I take my 3 points and I move them further and further away, things get bigger and bigger. And if I move them into them, it's a bit complicated. Now, right, one of the things we could do which is really useful, is say, all right, so between here and here, we have a whole bunch of math to do. And the first thing we can say is, I want the squares to get smaller rather than larger. And to do that, what we need to do is we just need to find the inverse of that number in a very similar way to what we did here. So we knew that if we took a number and divided it by, in this instance, 10, we will get a tenth. And that if we times that by 10, we'll get 1. So by going 1 over a number, which is usually quite large, we're kind of guaranteed to get numbers with a little bit more work, but we are kind of creating a domain of numbers that sit between 0 and 1. Now, I'm going to go to the maths component, I'm going to go to the polynomials tab, and I'm going to choose the 1 over x component, which does 1 divided by whatever the input here, x is. I'm going to put the distance into that, and now when we use that as our factor, you'll notice that we get something a little bit more sensible. Now I'm going to hide some of this stuff because we've gone through it. Preview off, and now we can see that most of the squares are fine. Hello, Chandra. Most of the squares are fine, except for the ones that are really, really close to the points. And the reason for that is that if we look at our drawing and we think about what happens as that point gets closer and closer, that at some point, let's call it this point here, the distance equals 1. And when we find the inverse of that, we do 1 over 1, which equals 1. And say here's the distance 2. 1 over 2 is something like 0.5, right? But as this number gets smaller, say it's 0.5 over 1, that number becomes 2. So we have a problem where we have to catch these numbers that are within the radius of 1 of this system so that we can make sure that these squares don't get too big. And the way we do that is that first off, we're going to open up our typing instrument and we're going to make a new little subplan that helps us kind of strategize how we're going to get there. So the first thing we're going to need to do is we're going to say, we're going to have to ask some questions, right? Is a number larger than 1? If it is, make it equal to 1. So now we have a system where no number can be larger than 1. And these are the two things that we need to approach and get sorted in order to kind of make this system a little bit more robust. Now, I'm going to click on the GH window, and I'm going to start getting onto that. So the first thing we need to do is figure out what numbers are larger than 1. And to do that, we are going to go to the maths category, and we're going to go to operators, and we're going to choose a larger than operator. And we're going to say, if this number is larger than the number 1, we want it whatever the output is. Now, if we look at a panel, you'll notice that this component outputs true and false values all the way through. So there's a true, but most of them are false. And what we're going to want to do is we're going to want to replace, we're going to want to find all of the numbers that are larger than 1 from this list. I understand that we have decided if a number is larger than 1 or not, and that's there stored in a list for us, but we personally haven't written an instruction to say, okay, when this value is true, I want you to do something. So what we're going to do is we're going to say, all right, I want to know the index of every true, right? That's a question that once we've asked that, we can say, okay, I want to know the index of every value that is true. After that, we can say, okay, now that I have all those indexes, make them equal 1. And that is a bit of a confusing line to say, but hopefully it makes sense as we kind of go through it. So, okay, larger than seems great. Now, I'm going to go to the Sets tab because we're dealing with lists of information at this point. And I'm going to go to the Sets dropdown, and I'm going to choose the Member Index option, which finds the occurrence of a specific member in a set and/or list in this instance. So I'm just going to drop that in. So the set we're going to look through is the list we just went through, and the member we're looking for is, I'm going to go to the Primitive tab, and I'm going to choose a Boolean, is we want to know when this condition is true. We're going to drop that in, and you'll notice that what we end up with is a series of indices. Now, I'm hoping to kind of eventually teach you guys trees through just like, you know, them just appearing again and again and again. But you'll notice that when we look at the original list here, that 0, 0, 0 is like the first one here has all falses, so there's nothing in it. The second one has all falses, so there's nothing in it. But the third one, which had the first true, has one thing in it, and it's saying that the index, the square at position 4 is the one that's larger than 1. So that's great. We've identified the problem case. Now, we know that we want to make whatever is at those indices equal to 1. So that seems great. I'm going to move back to my sets component. This time I'm going to go down to list, and I'm going to choose the replace items, replace certain items in a list. Great, so this asks for a list to modify. We got one of those. The items to replace with, we know that we want it to be 1. The replacement index for each item, well, we know that we want it to be 1. Sorry, we know that we got those indices from here, sorry. So they're the indices we want to replace. And then wrap is a particular component that allows the component to run different times if there's a lists mismatch, which in this case we don't have to worry about, but that will probably come up in a later video. Great. So here we are. I'm going to plug my list into here. That's the list I want to edit, the list of numbers. I want to replace my number with this 1 here. Great. The indices I want to challenge are these ones. And now, if we look at our original list here, and the fourth value is 1.915284, and now we look at this list, and we look at the same value, it now just equals 1. Awesome. What did you set the Boolean as, true or false? Okay, so that's an important one. Now, look at what this component is doing. This component is saying, is a number A bigger than a number B? And for most of the time, this is not true. The numbers that we're making are less than the number 1. The only time this will be true is if a number is larger than 1. So when we come to this component, what we wanted to decide was that I want to know the indices of every component. So I want to know the index of every true value in this series of lists. So the Boolean is, yeah, this, it can live there. Sorry about that. Teething problems. Every time you start something, you're going to have problems. This member index is we're wanting to get the index of every value that's true. So this Boolean is therefore a true value. Is that clear why that's true? Because there's two ways that you go about this stuff. You just try and copy what I've kind of put onto the screen, in which you don't really understand why I've done certain things, or you kind of, we sit down and we make it very, very clear why the code is doing what it's doing. Does that answer your question, Sarah? I'm going to assume it does. So cool. So now we've got this list with the value of 1 instead of 1.9, whatever it was. Great. And all we have to do is plug that as our factor. And you notice that it now limits the solution to 1. Awesome. And as we make the system bigger, why it's true. That's fine. Still trying to understand. I can just explain it again and again and again. It doesn't really matter. So this component here is asking, is a number bigger than another number? So is 3 larger than 1? Yeah, that's fine. That's true. Is 0.1 larger than 1? No, that's not the case. That is false. Now, we've identified that we get a particular type of problem when numbers are larger than 1, because we're taking the inverse of the distance. When a number is larger than 1, it's going to scale the thing up rather than down or not at all, which is actually the behavior we're after. So, knowing that, we're going to then sit there and say, well, what I really want to know and why I chose that larger than component was so that every time that a number is larger than 1, I want to know about it, I want to know where it is, and I want to set it to 1. Now, to do that, the first question we need to ask is, all right, cool. When is the result of this true? When is the scaling factor going to be larger than 1? Because this just outputs true and false values, right? So a whole bunch of falses, and we know that there's a true in the here. Did I move my points around or something? I think I did. 0, false, 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 false. 1, 2, 3, 4. Okay, so there's one in the 4th position. So let me just get my panel back, plug it in, and let's let that go all the way down to the 4. And you'll notice that there's a true there. Okay? Now, there's a true there, and these are the ones that are going to cause us a problem because they're going to make the thing bigger. So what this component is doing is saying, I want the indice of every true value. So these are all the indices of the true values in that list of stuff. And then once we understand that, we can run this replace items component, which takes a list, takes an item, which in this case is the number 1, and replaces every index with that. So all the numbers that are larger than 1, we have now set to 1. And then when we shove that into our scaling factor, we get a kind of a more attractive attractor grid. And as a consequence of using a number slider here, we can actually cut off fairly quickly that number, right? That number actually doesn't have to be 1. We can set that limit at 0.8. We can set it at 5, which would be a bit weird, but we can set it wherever we need it to be. Now, the next thing we might want to do is to be able to control the scaling of the fall off, the drop off, and a common one to use is the square distance. So what we might want to do is we might want to say, well, before we take the inverse, we might want to do something to the code. And I'm going to just go to my maths section, and I'm going to choose polynomials, and I'm going to just say, well, you know what, I'm going to square it. And when I square the distance and plug it in, you'll notice that it falls off much faster. And if I say, for example, take the square root instead, which is the inverse operation of squaring, it falls off much slower. And this is something that I might actually want to be able to control in detail. And to do that, we're going to use a evaluate component. And the evaluate component is set up pretty much for what we want to do straight out of the box. It will ask for a function to evaluate. It will ask for an x input, and it will also ask for a y input. Now, the x input, I'm going to give the distance. The y input, I'm going to actually give it a new number slider. So I'm going to make a new number slider, and I'm going to let it be a number between, let's say 0 and 3. And I'm going to put that into the y. Now, the last thing it's asking for is a function to run. And I'm going to make a panel component, and the function I'm going to ask it to run is x to the y. Now, what x to the y is x to the power of y, xy times. And because the square root is the inverse operation of squaring, the square root of x is just x to the half, right? Because a half times 2 is 1. So the inverse has to be a half to kind of maintain indice laws. And if you want to learn more about that, just hit me up. I'm happy to do a math video on it to make it really, really clear. But what this is letting us do is, if I set this to 0.5, nothing changes. But now I can actually control the fall off from no fall off to probably too much fall off. Pretty simply and easily. And now we've got a slightly more robust system. And this is what I meant by, okay, if we just do it first, we'll understand what math we need to do. Now, we're almost there. Like, this is almost over. We have one more thing to do. And that is, instead of scaling this geometry, which is, something we may want to do, we also want to be able to extrude it in a particular way as to get that particular effect that we saw in the precedent image that I showed in the beginning. Just so we're all on the same wavelength. If anyone came in late, that's the precedent that we're kind of trying to create a poor man's version of. So what we're going to do is we're going to say, well, okay, cool. At the moment, this is driving the scale factor. I'm going to make a new number slider. You're going to hear that phrase a lot. And I'm going to set that so each piece of wood is the same kind of cross-section. Because, if they're all the same cross-section, you can just cut them all from the same piece of timber, and you just have to put them in the right place. And I'm going to let the extrusion value be decided from the work we did, the mathematical work we did. Now, this is pretty straightforward. What we're going to do is we're going to say, all right, let's go to surface, let's go to freeform, And here we'll find an extrude component. And what the extrude component asks for is it asks for a base profile curve or surface. We've got one of those already. So let's just plug that in. And it's going to ask for a direction. Now, we can extrude this in the X, the Y, or the Z, right? So we need to be very on point about what direction we want to extrude it. Now, I'm kind of ripping off someone's roof, so I'm going to choose the Z direction. So under vector, I'm going to go to the vector subcategory, and I'm going to choose the unit Z. And I'm going to plug that into the direction. And then it's kind of as simple as plugging that into there, and we will get something out. Now, you'll notice that because my camera is on top view, I'm not really seeing anything. But if I go to my perspective view now, you'll notice that I have a whole series of these components, and I can change the fall off to get different effects. I can change the where we're clamping the top to get different heights there, but probably, and I can also change the width of the timber members. But what you can really notice is that there's no top to any of these boxes. So under surface, under utility, I'm going to just choose to cap the holes, using this cap holes component, giving me some solid boxes. Now, one last piece of control that you might be interested in integrating into the code is right here before we extrude it, we might want to say, well, actually, now that we've done all that stuff, the extrusion is always going to be like fairly short. Maybe we want to be able to multiply whatever number comes in by some other number, which could be, you know, to 4, and plug this multiplication into the Z vector, allowing us to control the scale of the overall system. Now, the last thing that we need to do, which we haven't done yet, is I'm trying to make a roof, right? And it's currently going up. So I'm just making a really funky floor. Now, what we would do is we would say, actually, you know what? Under vector, I can just use this reverse vector component. And I'm going to take whatever vector I've got, I'm going to plug that in, and now that vector, instead of pointing up, will point down. Can we do color scheme on the extrusions? What do you mean by can we do color schemes on the extrusions? Are you asking, can I color the extrusions based on how long they are? Or are you just wanting to color the extrusions? While he answers, that is pretty much it. We have a pretty funky roofing system. I mean, I know it's not perfect, but it is something that a kind of a beginner can get their heads around and use as a launching off point to get interested in parametric design for whatever practice or projects they might be working on. Okay, cool. So he's got back. He does want to color the extrusions based on how long they are. That's fine. We can do that. It might be a bit complicated if I hit a point on any of these questions where I feel like we've kind of hit a point where computationally we're going to have a problem, that it's going to be a bit confusing. I think after I do that is where we kind of end it, because I think people's brains might begin to melt, and melted brains is a surefire way that people don't continue with their learning. Now, effectively what you're asking is, can I take these numbers, right? The extrusions are just an effect from the numbers. Can I take these numbers and assign them a value between 0 and 255, for example, right? That's something that we can do. So, first off, let's let's go to params, and let's go to this gradient tool. So you'll notice that there's a gradient tool, and it's already done a lot of the work for us, right? It knows that the lower limit is a number, it knows that the upper limit is a number, and it also knows that we're going to give it a parameter that sits within that. And then one that's going to pop out is a color. So I just need to figure out what my upper and lower limits are, and I'm there, right? So, so luckily we know that our lower limit is always going to be 0, right? You know, that there's no way that in the mathematics we've produced that you're really going to get a negative number. Like you can't get negative distances. And we've only done multiplication fundamentally and division on positive numbers. So we're only ever going to get a positive number back, which sounds great. So, and we know that the upper limit is going to be whatever we crunched it to, multiplied by whatever this number is, right? It's impossible for a number to be bigger than that number. And then once we've multiplied it by that number here, it's impossible for it to be bigger than that number. So what we want to do is we want to get a new multiplication, and we want to say, okay, well, the upper limit is always going to be whatever limit we've set to the maximum size of extrusion before we've scaled it at the end by the scale factor. And then we can plug that into there. Now, the t value is just the response to this, right? And you'll notice that actually what's happening is we are just creating a second geometric kind of string. Yes, this is recorded. Like if I stuff up on the YouTube side, there's a history of that now, which I'm quite sad about. You know, that might be a problem, but I'll try and save it from YouTube immediately in case I accidentally tick a wrong box somewhere. And now all we need to do is color the boxes that color. And what we're going to use is we're going to go to display, and we're going to use a custom preview. And we're going to say, okay, well, I'm going to custom preview my geometry, G. It's asking for geometry to preview and a material override. So I plug the material into there, I plug my geometry into there, and you'll notice that it goes from a light pink to a darker pink. And if I choose a different gradient preset, let's say we go from red to blue, we get something like that. And there's also a option here called linear interpolation, which should kind of always be ticked in my opinion, but that's just my opinion. Now we've colored all of our components based on their heights. And I hope that makes a lot of sense. All good. Well, that seems to be the end of the questions, which is a bit of a shame. But then again, there are only 9 of you, and 3 people have just been like logged onto this browser for the last 4 days. So that's like, I doubt they're actually watching. But all good. So this has been a great little experiment. Hope everyone enjoyed it. Feel free to leave a comment in the comments of this or in the chat. I'm assuming I can access that after this, about what you'd like to see next. I'm assuming you guys, the problems you guys are dealing with, specifically will probably be more interesting than the stuff that I might come up with, which might be a little bit more abstract. But yeah, if you've got a problem that you're specifically working on that you're like, okay, cool, I want to know how to solve it, just ask. And if it's kind of at the complexity level that we're at right now as beginners, happy to. If it's a bit more complicated, I'll just put it on the back burner until I think that we've gotten through enough material, like enough conceptual stuff. And there's a back catalogue of tasks that people can go through to learn Grasshopper before we get to it. So that's all good. All right. Thank you, and I'll see you, I'm assuming, next week. Bye.